Today we are doing Unit 1, Lesson 5. Now we're going to sort of branch off from geometry and do more algebra. And I'm going to introduce you to 5 equations that we're going to use for uniform acceleration. Uniform acceleration meaning an acceleration is not changing. So let's look at this example here. Here we have a VT graph, so velocity time graph. And at some point in time, let's call it t1, we have a velocity v1. I'm not being specific with numbers because we're creating an algebraic equation here. And at some point of time t2, we have a velocity v2. Now, if you remember, the slope of a vt graph is an acceleration. So if we found slope, we can figure out that acceleration, which is rise over run, would be our rise, which would be v2 minus v1. And our run, which would be t2 minus t1. t2 minus t1 is our time interval. And then here we have final velocity minus initial velocity. So this is the equation for acceleration that I originally introduced to you when we did first introduced acceleration. You can rearrange it if you like. So this is the equation rearranged. Just multiply both sides by time and then add initial velocity. You can rearrange for different variables. This I'm calling equation 1. Now in equation 1 we have 4 variables: final velocity, initial velocity, acceleration, and time. But notice we know nothing about displacement. So when we're working with the algebraic equations, there are 5 different variables that we can work with: initial velocity, final velocity, acceleration, displacement, and time, all of which are vectors except for, of course, time. Now the first equation has all of those variables except for displacement, and you'll notice as we do the rest of the equations, every equation is missing one variable. So how can I find displacement then? Well, displacement comes from finding the area under this graph. So if we can find this area here, then we can get the displacement. Now this is a trapezoid. Now if you remember how to calculate the area of a trapezoid, it's just your first height here plus your second height here. You take the average of those heights, so divide by 2, and then multiply by the base. It's the easiest way to do it. If you want, you can try this yourself later, but you can find the area of the triangle and add the area of the rectangle, and you'll get the same equation we do here. So when we plug in our 2 heights as initial velocity and final velocity, here we get our second equation. And this equation is missing our variable for acceleration. Okay, so we found the slope and we found the area. So where do the rest of the equations come from? Well, let me show you how we get equation 3. So I rearranged this equation for acceleration, and what I'm going to do is I'm going to take that equation for final velocity and substitute it in for displacement and see what we get. So I'll do this on this side here. So we'll have displacement equals initial velocity plus final velocity, which I will write as initial velocity plus a delta t all over 2, and that's still multiplied by delta t. Okay, well, I can simplify that a little bit because we have 2 initial velocities. So I can write this as 2vi plus a delta t all over 2. But what I can do with that 2 is make it 2 separate fractions like this. All times by delta t. And then I'm going to distribute the delta t. In this fraction, the 2 will cancel. So I'll get delta d equals initial velocity times time plus 1/2, that's the over 2, a, and then we have 2 times, so times time squared. Notice that's our third equation. And in this equation, we're missing the variable for final velocity. Now you can get equation 4 by doing something very similar. Instead of solving for initial velocity, instead of solving for final velocity, solve for initial velocity, substitute, and you will get equation 4, which is missing our initial velocity, because that's what you substituted with. And similarly, if you solved for time and substituted in for time, you get an equation that is missing the variable for time. One thing I want to mention about equation 5 is you'll notice in equation 5, unlike the other equations, we actually multiply 2 vectors together. Now, I haven't actually taught you how to do that, and we're not going to go in great detail, but we have to be careful with the signs. So if you have 2 vectors that are in the same direction and you multiply them, you're going to get a positive value. Whereas if you have 2 vectors in opposite directions and you multiply them, you're going to get a negative value. So for final velocity and initial velocity, well, if you're multiplying a vector by itself, obviously they're in the same direction, so it's positive. You don't really have to worry, because even if you accidentally throw in a negative, you're squaring it anyways, so you're going to get rid of that positive. Over here, with the 2a delta d, let's say, for example, acceleration is down and displacement is up. Well, then their product will be negative. And it's even okay if you throw in, let's say you label up to be positive. So this would be positive and this would be negative, and you can kind of see how that would work out. Because when you multiply a positive value and negative value, you will get a negative value. So just like we did before, when we first started way back, before we did all this motion graph, I think it was almost our first lesson. Yeah, our very first lesson, when I would write directions like left and right, and we would change right to the opposite sign and make it left for opposite vectors. And then we came up with a coordinate system, and instead of writing left, right, we put in positive and negatives. We're going to have to do the same thing with these equations. Where was I? With these equations here. Because again, we are going to be adding and subtracting vectors. So you are going to have to make sure you write a little coordinate system, like I did down here. For example, up being positive, or if your acceleration is left and right, label right to be positive, and anything that's left or down, make sure you put in a negative value for that. So as we go to solve an example problem, I'm going to remind you of the grass method. We've learned this in grade 9 science, and usually when we did like Ohm's law, you probably learned this in electricity, and you were probably referred back to it again when you did grade 10 optics, or maybe when you did chemistry and did density or thin lens equation in optics. Right? It's a good method to use to problem solve. Right? So we have given information, required information, then you analyze, so you figure out, okay, which formula do I need, solve the formula, and then paraphrase. Paraphrase is important because I feel like physics is a course in translation. You're literally taking a question, which is in English, translating it into mathematics, solving it, and then once you have an answer, translating it back into English. So let's try using the graph method to solve this problem. And I'm not going to require you to always write G-R-A-S-P for everything, but you should be writing everything down. And also, what I want you to include in analyze is to add a coordinate system, not just equation. Add a simply because we are now using vectors for everything. All right. This example says a car requires a velocity of 32 meters per second by accelerating at 4 meters per second squared for 5 seconds. What was its initial velocity? Okay, so what are we given? We're given here requires a velocity, so this is final velocity. So let's write final velocity will be 32 meters per second. This is acceleration, so we know acceleration. That's 4 meters per second squared. And it doesn't say that's time, but you can always, if you're unsure what a given information is, look at the units. The units can really help you tell you what it is. So this is 5 seconds, so we're given time. Those 5 seconds. All right, so that's our given information. Required says what was its initial velocity. Initial velocity is what we want to find out. So that's what we're required to find. And that's very, very important. I find a lot of times students try to read through the problem quickly so that they can get down to solving it. But if you read through it quickly, you can make, I see a lot of students make mistakes simply by misinterpreting the question. So G and R are very important points. Now analyze. We need to figure out what equation we're going to use. And remember, all the equations each had one missing variable. And out of all these variables, the one that we're missing is delta D. So we're missing the displacement variable. So let's go back and figure out, okay, which one of these equations are we missing delta D for? It's actually the first one. So let's write down the first equation then. My pen. So VF equals VI plus A delta T. Okay, now we need to solve. So what we need to do is rearrange the equation. And what I recommend you do is rearrange the equations before substituting. It's a hard thing to do because I know once you have numbers, you love to substitute those numbers, and numbers you're so used to and so they're so easy to work with. But I want you to try actually rearranging all the variables to what you need to solve for. In this case, initial velocity first, and then substitute. So what do I mean by that? Well, let's isolate for VI. So to do that, we're going to subtract A delta T from both sides. So we're going to get VF minus A delta T equals VI. That's it. That's all I mean. Seems like a small thing to ask for right now, but as problems get more and more difficult, it's going to be a very good skill to be able to rearrange variables as opposed to numbers. So now I can substitute, and I like writing what I'm solving for on the left side. That's just habit. So VI equals VF, which is 32. So 32 meters per second. Okay. And it looks like everything is going forward. So I can just have my forward direction as being positive. Since everything's going forward, we're not going to have to worry about changing anything to a negative. But it's important to get into the habit of writing that coordinate system down so that you don't forget a negative if one exists. So 32 meters per second minus acceleration, which is 4 meters per second squared, times time, which is 5 seconds. Okay, and now we can just solve. So this gives you 32 meters per second minus 4 times 5 is 20 meters per second. One of the seconds will cancel. And 32 minus 20 is 12 meters per second. Still positive, so still forward. Then you can write therefore, translating it back into English, the initial velocity of the car was 12 meters per second